All right, we're back at Math 676. I would like to talk about the Step 3 tutorial program of deal.II. That's the first program where we actually solve a partial differential equation. And I would like to introduce you to the sort of things that you have to do if you actually want to solve something. So far we have seen how you construct a mesh. We have seen how you would enumerate all the degrees of freedom on a mesh. And so the next step, of course, would be to build on the matrix structures that we had built, so the sparsity pattern of the matrix that we had built in Step 2. And now I would like to talk about how to actually build the matrix that results from the Laplace operator and to solve it so that we get a finite element solution out of this. So Step 3 is a program that is not very long either. It has maybe 100 lines of code, and what it will do is it will set up the linear system. So we had already seen how to build the sparsity pattern of the matrix. It will actually compute the matrix. And then how to compute the matrix based on the operator that we want to solve. That will involve that we have to loop over all the cells, and we have to use a class that is called FE_values that I'm going to talk about. And then once we have this linear system, we need to solve it, which we will do with the conjugate gradient method, and we have to visualize it so that we can actually get some insight into how the solution actually looks. So before I show you the program, one of the things that I need to talk about is the following. So when you write the bilinear form in a mathematical way, then you see that the matrix entry Aij equals the integral of gradient phi I times the gradient of phi j. And I had talked about this before, that we typically write this as a sum over all of the cells. Now, you could think about this then in the following way. So in order to compute this matrix, I'm going to let's say if I have 100 degrees of freedom in my mesh, then this matrix is going to be 100 by 100. And one of the things that I could do is I could have a loop over all the i's, and I could have a loop over all of the 100 different j's. And then for each one, as in this double loop, I would have a loop over all of the cells, and I would integrate over on every cell this gradient of phi I times gradient of phi j. So let's say I have 100 degrees of freedom on, for example, 80 cells. Then that would be the outermost loop over I would run over 100 iterations, and the innermost, the middle loop over j would run over 100 iterations, and the innermost over all the cells would run over 80. So we would have a total of 100 times 100 times 80 equals 800,000 inner iterations that we have to go through. That turns out to be terribly wasteful. And the reason for this is that if you look at this a little bit closer, so on every cell k, when you look at this integral that we have to form on a cell k, the gradient of phi I times the gradient of phi j, it turns out that only very few of the phi i's are actually non-zero on this particular cell k, and only very few of the phi j's are non-zero either. So in reality, this integral over k of gradient phi I, gradient phi j will be non-zero only for very few i's and j's. And we can say exactly which ones these i's and j's are for which this term is non-zero, and namely these are all of the degrees of freedom that live on this cell. So the finite element method, as I mentioned before, is a local method. Every shape function lives on exactly the cells that surround the vertex that is defined on, or if it's defined on an edge, then on all of the cells that are adjacent to this edge. And so, in essence, the only i's and j's that we have to consider when we integrate over k are really the ones that are defined only on this cell. So if you are on a triangular mesh, for example, and you use a P1 finite element, then we know which ones these are, namely the three shape functions that are defined on this one cell. If you are using a Q1 finite element on quadrilaterals in 2D, for example, then you know exactly which ones these are, namely the four shape functions that are defined on each one of the four vertices of the cell. So in reality, out of these, let's say 100 by 100 entries for this matrix A, if I have a total of 100 degrees of freedom, on any given cell, only 4 by 4, namely 16 matrix entries, are non-zero. And the way we compute this, therefore, is not that we have a global sum over I and a global sum over j, and in there a global sum over k, but we do this the other way around. So we loop over all the cells k, and on every cell we identify which are exactly those 4 degrees of freedom that are non-zero, and then we're going to build a dense 4x4 submatrix. And so that means that, let's say, if we had 80 cells, then we have to build on every cell a 4x4 dense matrix. That means 16 times 80, that is 4,800 entries that we have to compute, right? 16 entries on every one of these 80 cells, 4,800 entries that we have to compute, rather than the 800,000 that we had before. So it's much more efficient to do it this way. And then what we're going to do is, so we built this 4x4 dense submatrix, and then we do an operation that we call distribute, which essentially means that we identify for each one of these 4 shape functions that live on this cell, what is the corresponding entry, let's say, from in the global matrix where this local contribution from this cell k has to be copied into. That's what we call the distribute operation. And we can do a very similar thing for the right-hand side, where we build a local vector for the right-hand side that has only 4 entries, namely the integral of phi I times f, where f is the right-hand side. And after building this dense vector of 4 elements, we distribute it into the corresponding elements of the global matrix. So let me give you an example. So let's say we are currently sitting on, so we have this loop over all of these cells, and we're currently sitting on cell number 4. We identified it, so this would be cell number 4. And so the degrees of freedom that are living on this cell number 4, that is the shape functions that are non-zero on this cell, are only shape functions 1, 3, and 5. All of the other shape functions are 0. Okay? So in this case, what we need to do is we need, from this particular cell here, we need to compute the contributions to the matrix entries A11, A13, A15, and A33, A31, A35, and A55, A51, A53. That's exactly 9 entries for a that is a 3x3 dense matrix that we can then later add into the global matrix. You remember that the global matrix is a sum over all of the cells, so the distribute operation adds the local contribution from a cell into the global object. So that's roughly the way we're going to work. So we're going to build, let's say, if we had triangles like here, a 3x3 dense matrix. If we have a quadrilateral and a Q1 element, a 4x4 matrix, we're going to make this a little bit more generic. We're going to say, okay, we're going to ask the finite elements, how many degrees of freedom do you have on a particular cell? And the finite element, if it's a Q1 element, is going to return, hey, I've got 4. But if it was, for example, a quadratic element, it would return 9. If it were in 3D and it was a quadratic element, it would return 27. So we're going to build a dense matrix on every cell that has size, we call this DOFs per cell, by DOFs per cell. That's the number of degrees of freedom per cell. And so we're going to build this locally as a sum over I and j, where I and j goes from 0 to DOFs per cell. And then around this, we will have a loop over all of the cells k. So that's the first part that I need to talk about. The second part goes like this. So I told you also earlier that we never compute integrals exactly, because principally we cannot. So when we built these local contributions on a given cell k, aij is the local contribution, and we have to add them up for all of these cells. So it's going to look like this. So it was the gradient of phi I times the gradient of phi j integrated over k. And you remember that phi I and phi j were defined on the reference cell. So these are polynomials on the reference cell. But, and I see this is actually a mistake, it shouldn't be the gradient of phi I hat and phi j hat, but it really should be phi I and phi j. Phi I hat are on the reference cell, but we really integrate on the real cell. So phi I and phi j on the reference cell are polynomials, but if you map them, they're still polynomials. But if you take the gradient, you have to multiply this with the inverse of the Jacobian of the mapping, and that is a rational function. So the integrand that we have here is a rational function for most arbitrarily shaped cells. So there is no real good way to really integrate rational functions exactly. And what you have to do in order to do this is you have to use quadrature. So we will replace this integral here. We've done this in one of the previous lectures. There's a couple intermediate steps, but ultimately you come out with this particular formula here, where this term at the front here is the integral, is the gradient of phi I in the real cell coordinates. This here is the gradient of phi j in real coordinates, and over here I have the determinant of the mapping times the weight of a quadrature point. And I've talked about this before, that these two terms always appear together, and so we're always going to abbreviate this as jxw, j as in j times w. So one of the things that you realize when you look at this formula closely enough is that it looks like we have to evaluate functions at arbitrary points, at these xq hats. These xq hats are the quadrature points that we get, for example, out of a Gauss quadrature formula or out of the trapezoidal formula. But if you look at this closely enough, it turns out that a lot of the things that are happening in this formula you don't really need to evaluate at arbitrary points. For example, if I use a Gauss quadrature formula on every cell in my mesh, then the set of these xq's is going to be the same at every cell, because I need to evaluate this phi I on the reference cell, for example, on the quadrature points on the reference cell. And of course, the quadrature points on the reference cell are always the same, no matter how many cells I visit. So each one of these cells might be differently shaped, and it might be a translation and a rotation and a shearing of a previous cell, but the quadrature points on the reference cell are always the same. So in other words, if I have to evaluate these shape functions on the reference cell, that's what the hat indicate, on these quadrature points, then this is an operation that is the same on every cell. If I need to evaluate the gradient of phi I on these quadrature points, it also is exactly the same every time. The only thing that changes from cell to cell is the inverse of the Jacobian of the mapping, this j to the minus 1 here. That is something that I really need to evaluate differently every time. But so ultimately what I want to say with all of this is the following. So a lot of the information that goes into this formula is something that we can reuse from cell to cell to cell to cell, and that there is a very structured approach to this, that a lot of the information here happens to be the same, or happens to be recomputed, happens to need to be recomputed on every cell. And so because this is so, because I do not need to evaluate most of these functions at arbitrary points, but because they always need to be evaluated at quadrature points, one of the abstractions that I can make is that I introduce another class, and we're going to call this fA_values, that provides exactly the sort of information that you need if you want to do numerical quadrature. And in particular, what this is, it is going to be the values and gradients of the shape functions evaluated on the reference cell at quadrature points. So this is a piece of information that requires information from the finite element and from the quadrature formula. And then it needs to be able to provide us something like the inverse of the Jacobian matrix, this j to the minus 1. And that is something that requires the quadrature formula and an object that describes the mapping from the reference cell to the real cell. So for example, what you've probably seen in your finite element classes is that you use a linear mapping to map triangles from the reference cell to the real triangle. For quadrilaterals, we use bilinear mappings. But you can use higher order mappings too. So for example, if you want to use curved boundaries on your domain, then you would use a quadratic mapping or a cubic mapping. And so to compute this j to the minus 1 at a quadrature point xq would require us to know something about the mapping and about the quadrature formula. So this FA-values object that we're going to introduce has the role of providing us exactly what we need for the numerical quadrature, and to take together the information that is provided by the quadrature object, by the finite element object defined on the reference cell, and by the mapping object. And so these three things together is what goes into the FA-values, and you will see this in a minute when we look at the code. I should mention the following. So this FA-values object does not give us this and the gradient and the Jacobian separately, but we will ask the finite element, the FA-values object, to give us the product of this whole thing here. However that computes this sort of information is not really our concern. It's just going to give us the gradient of the shape function on the real cell, on cell k, of shape function phi I. It's going to do the same thing. This whole term here is going to be the gradient of phi j on the real cell, and then it's going to give us a jxw value, which takes on the role of something like the dx in the integral. So with this, let me show you how this step 3 program actually looks like. As before, here's the link where you can find it, and the steps to make it run are always exactly the same. I'm going to show you in the next lecture then how to visualize this, the solution. So let me show you the actual program. So if you go again to the deal.II website, you click on whatever version you're interested in, you click on the tutorial, you select program number 3. So again, as before, it has the introduction, which is extensive. It has a lot of documentation in the program itself, and then at one point there will be a results section that shows the solution, and then it has a section where it just shows the program. I should mention this. So it solves the equation minus Laplace u, I have this at the top here, minus Laplace u equals 1 on the unit square with 0 boundary conditions. Okay, so the program works like this, and step 3 is the first one that shows essentially the structure of all of the following programs. Namely, we create an object of type step 3. We call this object Laplace problem, and it has a public member function run, and that does all of the important stuff. So let me show you the class declaration real quick. So the class declaration looks like this. So it has a public constructor and a run function, and that's the entire public interface. Typically, one of the things that you try to do in software engineering is to hide as much information as you can from the public interface, and that's exactly what this thing does. So then within this class here, it has 5 member functions, namely a function that makes the grid. You've seen this. This is essentially the first grid function of step 1. It creates a triangulation that corresponds to the unit square. Setup system will distribute the degrees of freedom and set up the matrices and so on and so forth. Then there is a function that assembles the linear system. That means to do the integration. Then there is a function that does the linear solve, and then there is a function that does the output, or that generates an output file. And on top, so this is basically the structure that every one of these tutorial programs will have. And if you look at the run function of this class, you will find that it calls essentially just these 5 functions one after the other. Let's take a look at the other variables that we have in this class. So in the step 3 class, we have a triangulation object, we have a finite element object, we have a DOF handler object. That's the object that keeps track of which degree of freedom on which cells has which number. Then it has an object that describes the sparsity pattern of this matrix. You've seen in step 2 how to build this. Then it has the matrix of the linear system and the solution and right-hand side vectors. And so without further ado, let me jump right through the setup system function. You've seen the make grid function in the first tutorial program. So in setup system, we have already built the triangulation, and the DOF handler has also already been attached to the triangulation. So what we do is we distribute the degrees of freedom. That is, we enumerate all of the degrees of freedom. Then we build the intermediate sparsity pattern like we did in step 2, and then we copy it into the final location. That's the sparsity pattern variable. And so the only thing that remains is that we build a matrix that's based on this sparsity pattern. So that's what we do here. System matrix dot reinit sparsity pattern. So we set up a matrix that is able to store elements in exactly those places where the sparsity pattern indicates it. And then we reinitialize the solution and right-hand side vectors to have a size exactly equal to the total number of degrees of freedom. So that's the setup system function, and then the next one that we need to call is assemble system. That is the one that actually builds this matrix A and builds the right-hand side vector F. So when I say build, it fills the entries of this matrix. And there's a little bit of boilerplate code going on here. So what we do is we first select which quadrature formula we want to use. So we use a Gauss formula with 2 quadrature points per coordinate direction. So we're in 2D, right? So that was the this here. So we're in 2D. That means that this quadrature formula has a total of 4 points, 2 in x direction and 2 in y direction. And then with this quadrature formula and this finite element, we initialize an object of type FA_values, and FA_values will provide us all of the things that we need for the computation of the individual entries of this matrix A and of the corresponding right-hand side. And FA_values can provide a lot of information. So one of the things that we always do is that we try to restrict the information to what we really need. It can provide much, much more than what we need for this particular program. It could compute normal vectors and second derivatives and so on and so forth. And it would all be very expensive if we computed all of this. So we say exactly what we want. Namely, we want to have the values of shape functions. That's something that we need for the right-hand side, where we need to compute the integral of phi I times f. We need to have the gradients of shape functions. That's what we need to compute gradient phi I times gradient phi j. And then we need these jxw values. And then what we do is we build a full matrix of size DOFs per cell. That's, for example, for the Q1 element 4. So this matrix is going to be a 4 by 4 vector matrix, and we build a local vector of size 4. These are the contributions of a particular cell. And I'll come back to this local DOF indices. So what we do then is we have a loop over all of the cells from the first to the last active cell. And what we do on each cell is we tell the FA_values, please recompute everything that is necessary among the things that I told you above in order to compute these matrix entries. Then we set these local matrices and right-hand sides to 0. And then we have here this loop over I and j from 0 to 4, for example, if we have a Q1 element, and a loop over all the quadrature points, which in this case is also a loop from 0 to 4. But you see that I never write 4. I always use these symbolic names, DOFs per cell, so that it's easier to change this. And then we compute, for example, the local contribution of the cell matrix from one quadrature point as the product of the gradient of shape function I at this quadrature point times the gradient of shape function j at this quadrature point times jxw at this quadrature point. And we do the same thing for the right-hand side, which is the value of shape function I times the value of the right-hand side, which in this example is 1, times jxw. So this is in essence the entire assembly loop for A and the right-hand side. And then there was this operation where we needed to distribute the local contributions into the global matrix. And this works like this. So we get the global numbers of the shape functions that are defined on this particular cell. So in the example that I showed you earlier, it was 1, 3, and 5. And what we're going to do is we're going to have a double loop over I and j from 0 to 4, from 0 to 0, 1, 2, 3, where we're going to copy the local element cell matrix Aij into this global matrix at position local DOF indices I and local DOF indices j. So local DOF indices is the global numbers of the shape functions defined locally on this particular cell. So this is local DOF indices in the example was an array that had elements 1, 3, and 5. I and j loops through 0, 1, and 2, and so this copies into the global matrix. And we do the same thing for the right-hand side. There's a little bit of work that we still have to do. So you know that the Laplace equation is not well defined if you don't pose the appropriate boundary conditions. And so in this case, we form 0 boundary conditions. And there is essentially 3 function calls that are necessary to deal with this. And I'm going to skip over this here in the interest of time. But if you read through the documentation of step 3, it will be explained what this means. So at this point, we have the appropriate linear system. And we can hand it over to the linear solver. So we have A and we have F, and we want to solve AU equals F. One of the easier ways to do this is to use the conjugate gradient method. So we need an object of type solver CG for conjugate gradient. And the CG solver needs an auxiliary object that we call solver control that says this is the maximum number of iterations you're allowed to use, and this is the tolerance I would like to achieve. So in this case, we ask that there is no more than 1,000 iterations, and that we terminate iterations when we are at a tolerance of 10 to the minus 12. And so with this, we can call solver.solve with this particular system matrix with the solution vector and the right-hand side. So this is AU equals F. And then typically for these iterative solvers, you need a preconditioner. In this case, we just use the identity preconditioner. That means no preconditioner at all. So at the end of this function, this variable solution here should have the correct answer already in it. And then the last thing that our run function does is it calls output results down here. Output results does something like this. So there's an object in deal.II that is called data.out that wants to know about the mesh that we work on and the degrees of freedom. So we say attach to your F handler. And then you can add vectors that you want to output into this file. So in this case, the only vector that we're interested in is the solution vector. But you could repeat this one call to add data vector here. And so what we would like to do is that this vector with these elements defined on this DOF handler is going to be written into the output file under the name solution. You can choose whatever solution you want here. So oftentimes we just say U because we typically denote solutions by U. And then there's a function call function called build patches that transforms the information from the mesh into some sort of intermediate format. And then these 2 functions here will write this intermediate format from the data.out class to an output file in GNU-plot format. And I'm going to show you in the next lecture how to visualize this in GNU-plot format and then later on in a slightly more sophisticated format. So at this point, you have solved your first PDE and you have outputted into a, let's say, file for visualization purposes. And from there on, we can go and solve more and more complicated problems. But that was really all that was necessary to solve a Laplace equation. So far, on a square mesh, on with a Q1 element, but you have seen that if we just change the mesh, for example, here in make grid, then that you could immediately solve something on a more complicated domain. I should also mention that if you had changed FE1 here, the polynomial degree from 1 to 2, for example, that you could have automatically solved something with quadratic elements. So with this, I'll leave it here for now. As I always mention, it's worth playing. So take the suggestions that we have at the bottom of step 3. And then in the next lecture, I'm going to show you how to visualize the solution that we get out of this program.